Good morning, students. Today we're going to explore chapters 10.3 and 10.4 of our textbook, where we talk about signed numbers and connecting them with addition and subtraction. When we get together again next time, we'll talk about signed numbers again, but we'll focus on multiplying and dividing. But today it's about adding and subtracting with the primary use of a certain specific model called the CHIP model. And we're going to go through how to use the CHIP model and examples with the CHIP model. And then when you do your website homework, you'll see that there are questions associated with the CHIP model there as well. Some important announcements before we begin. There is an extra credit opportunity for you if you go to the folder in e-learning Blackboard, the one that is Unit 4. If you go in there, you'll see there is an extra credit opportunity, and you can send it in an email to me. I'm accepting it up until the last day of class, which for you guys, that means December 10th, I believe. And it's a couple of extra essays to get some extra points on a lower graded exam. The other important announcement I have is you guys did very well on the last exam. I'm very proud of you, but well done. Please keep up the work. And we're looking forward to working with you on the 5th exam, and hopefully Structures of Math 2 is coming, and you'll take that next term, hopefully with your favorite teacher, Mr. Marquetta. Something else about our class that we should mention today is that today we have a lesson, and on Thursday we have a lesson for the remainder of chapter 10, but then that's the last lesson. So Thursday is our last lesson, and next week on Tuesday we're going to be doing essays and activities and last minute questions, and then our last exam will be, of course, next Thursday. So we're wrapping up Structures of Math 1, and I do enjoy very much working with you guys. So just get ready for the end of our term is coming, and just prepare for that and keep in touch about those ideas. Okay, that's kind of all I have for our introduction. Let's begin talking about chapters 10.3 and 10.4 now. First, the age-old question, when am I ever going to use this, comes up. So it's kind of important that we have an answer for that for our students. We want our students to feel like the material we are delivering is practical and usable. And for example, negative numbers is very practical. They may not necessarily see it right up front, but it certainly is. For example, in financial matters, negative numbers play a role. Plus and minus means something special in financial matters. The idea of debt and owing, the idea of what it means to own a house, to own it outright, or to have equity or debt, things like that. We have signed numbers that play a role in those explanations. Also, temperature changes and sea levels will appeal to the scientist in our students, and that's something that interests certain students more than others, that they are interested in geography or oceanography, these different ideas. So you can use negative and positive numbers to discuss temperature changes, and also to discuss what sea level means. And then, of course, there's the physical education aspect. In sports, there's some negative number ideas, like in football. You could talk about what it means to advance yards versus to go back yards for the game. And then golf is the idea of trying to keep it as the lower score. Like, for example, in golf, if you and I were playing golf, you would win if your score was lower, because it's how many times did you have to hit the ball to get it to fall in the hole, right? So like, for example, in golf, if I only had to do 2 putts and I got it in the hole, when you had to do 5 putts, like, I did better than you. So the point we're trying to make is lower numbers are better in golf, and that's another way to express positive and negative numbers. With regard to diets, there's caloric intake and how many calories are associated with any food, and then how that can be adjusted and changed according to different plans and diets. Also, the idea of gaining and losing weight is positive and negative integers. That's part of dieting. So you could bring up that idea. There's atomic charges, which have something to do with plus and minus. And again, that's the scientists and our students. And then the games where you can go in the hole, like golf. You could also use skee ball as a good example for a go in the hole game. But all of these 7 ideas all 7 of these things are reasons why you should learn the positive and negative numbers, and you can use it in your discussion in a human way with your students. Like, why do you need to know? Well, these are some of the things that use negative and positive numbers, so we need to get good at them because we want to be fluent in how they work. And anytime it comes up again, like, oh, I understand what -4 means. I can think about -4 meaning 4 miles below sea level, or losing 4 pounds this week, things like that, and associate it with these different ideas to make students comfortable with positive and negative numbers. So now let's talk about the colored circle model. It's also called the chip model. You could call it the colored circle model or the chip model. We can use different colored chips to represent negative and positive quantities. We're going to use yellow chips to represent positive numbers, okay? And we're going to use red chips to represent negative numbers. So if you'd like to think about +3, you can draw 3 yellow chips. If you want to talk about -4, you can use 4 red chips. Now, in the same conversation we're having here, let's discuss that you can do this with blocks that have letters and blocks that have numbers. You could do this with Play-Doh that's purple and Play-Doh that's white. You could do this with yellow markers and red markers. You could do this with crayons. You could do this with candy. You could do this with all different kinds of things. And you can tell the students that every day when we study integers, you're going to pick a new thing for pluses and a new thing for minuses. Okay, well, this time it's going to be maybe paper clips and I don't know, thumbtacks or something. Well, not thumbtacks because they're sharp, but you know what I mean. Like, the point I'm trying to make is you can apply this to any kind of learning style. You could do this with tactile learners, with blocks and things like that. You do this with visual learners. In this PowerPoint, I designed it to have animation so that the circles move around. So the visual learners will have a little bit more of an impact. You could do this with audio too. You could recite out loud 1, 2, 3 yellow chips, 1, 2, 3, 4 red chips. Everybody, 1, 2, 3 yellow chips, and you get your students to do that. And what happens is there's learning happening in between there that you might not even see. Okay, so what is the colored circle chip model, my friends? It's that yellow is the pluses and red is the negatives. Okay. So let's talk about what 0 is, because 0 is kind of the focus of the colored chip model. And if you can at any time make them match, you can cancel them out, and that's the idea of 0. So here's an example of 0. It's 0 because it's an equal amount of yellows and reds, or an equal amount of blocks with letters and blocks with numbers, etc., etc. Like candy canes and Twizzlers, or something like that. Pick 2 things, that are different. If you have a match of them where they have exactly the same quantity of each, you can say, okay, well, that's 0. And you can build on 0 in different ways to express and represent different quantities that are both positive and negative, using this idea that 0 is shown by using the same amount of chips for both colors. Here's another example of 0. Here's another example of 0. So all 3 of these images you're looking at are examples of how to express 0. This is a gain of 2 followed by a cancel of 2, or a gain of 1 can be canceled by a loss of 1, and so on. So that's what we mean by 0. They're equal chips. And if you focus just on the middle one, you'll see that every time you have a pair and you can pair up a yellow with a red, you can remove it from the story, is the idea. So let's talk about the number -3. The first idea we think about with -3, of course, is this. But you can also use that idea of 0 to add 0 on in many different ways. Like this is 3. See how I've added 0 on? I've added 0 on in yet a different way here for 3. And you can do this in many different ways for many different reasons. For now, we're just doing adding and subtracting, so you won't see very much of this. But when you do other things like multiplying and other kinds of operations using the red chip model, sometimes putting them in different arrangements like this, it gives you an advantage and gets the answers to you quicker. And that's the idea. It's supposed to be a tool to bring you to an answer quicker that way. Okay. Another thing that we like to do a lot here with the colored chip models is use a box. So let's get a box. Here's a box. Now, in the box, we could put the idea of 3, and then we could put the idea of -3 as well in the box. And now what happens? Well, I guess they cancel each other out, and what's left in the box, is nothing, so the answer is 0. This is the idea of the box. So you draw a box. You take each of the things that the equation says very carefully. It says 3, so you put 3 yellow. Then it says plus -3, so you put 3 red. You look in there, and you start doing your tactile learning and touching the chips and playing with them. And when you pair them and touch them together, they vanish, and they all vanish because everyone has a partner and they're all gone. So, that little story problem associated with it helps the kids to get familiar with how integers work. So here we're asking, again, for more cases, but you'll notice that in this situation, both of these questions are addition questions. They both have a plus in the middle, right? However, they also both have the same sign. The numbers have the same sign. They may be different in the first one, they're positive, in the second one, they're negative, but they are the same sign. This is associated with the model of addition that we discussed already. That's called treating negative numbers as positive numbers. It's connected to that same concept. Because in the chip model, what happens is you basically do the same thing, it's just different colors. For +3 plus +2 ought to look like this, giving you 5. But for -4 plus -3, it ought to look like this, giving you -7. It's the same exact idea. It's just that you're treating the negative numbers like they're positive numbers and using a different color chip to represent debt instead of gain. So, we can use this idea to get the students to start thinking about how when you add a negative to a negative, you just add and you keep it negative, or any other conjecture that comes along with this concept of what it's like to add something like -4 plus -3. That's a very strong tool. It helps students to see things that we might not have been able to bring across in words or writing on a chalkboard. Now, what if the signs are different? Well, you use the additive inverse idea and you wind up canceling things out. So if 3 and plus -5, of course, you get 3 in the box, and then you get -5 in the box. And once again, you consider how we could do pairs and partners, and there's 3 sets of pairs there that could kind of cancel each other out. And what's left, right, is the 2 red dots. This is another great example of how to use addition and plus and minus numbers to get answers with red and yellow chips here. And that's the model. The answer is -2. Here's another great example. -2 plus 6. I think you know what it ought to look like. We'll do 2 reds in the box, 6 yellow in the box. And then we have a couple of pairs. And then we're left with 4 yellow. And that means, of course, +4. Something else that we should just mention while we're talking about using this manipulative. As with any manipulative, whether it be a strip diagram or an array model or any of the wonderful things you learned in structures, remember before you start barking at the class that you know what the answer is. Like come back for a minute. Before I start talking to you about how this is going to work, I already know in my head 4 is the answer. And I know 4 is the answer because either I went through this PowerPoint before I talked to you, which I did, or because I used my own higher level thinking to do arithmetic in my own way as a teacher and an adult to see the answer's 4, regardless of what the chips say. But the point I'm trying to make is before you start teaching it, put the example on the board and just in your mind for a second say, yeah, the answer's 4 to this one. And then carry on. Okay, we'll get a box, we'll put 2 in, we'll put 6, and you keep, but the point I'm trying to make, my friends, is if you're going to teach and be effective, you got to kind of know what the answer is before you start talking. And I think that's very helpful. And sometimes I find myself making that mistake of putting a long equation on the board and talking about factoring and graphing and vertex and intercept, and I go into this whole thing. But before I start doing it, I should have known that the answer was 5x minus 8, just in the back of my mind as I'm doing it to make sure I'm doing it right. 5x minus 8 is the answer. See what I'm trying to say? And that doesn't just apply to math. That could be if you're talking about The Great Gatsby in literature, or if you're talking about, painting in your art class, or whatever you're studying and teaching. Know what you're expecting the correct answer or the best assessment to deliver to be. For example, in this question, 4 is the answer, and that's in the back of your head. It's educational ideas, just try to keep them going. Now we're going to look at this case where we have signed numbers can be added and subtracted using a number line. Now what you're looking at here is an alternative case that's different than the colored chip case. And I'm going to explain it to you because it is in your textbook, and there is a little bit of practice when it comes to WebAssign associated with this. I'm going to just put the picture up first, and then I'll explain to you how to get to the answer. Again, like I said in the last slide, I'm expecting to get 15 here, right? And I think I know that because I took Algebra 1 in high school, because I understand minus means plus, and the kids don't know that minus means plus yet. They're still exploring the chips, and you're letting them discover things on their own. So they don't know yet necessarily that you could do that shortcut, but I want you to keep in your head, my friends, what's the answer? N is 15, right, for this? Just keep that in your head and look at what the number line is and how you can get there. Now, how could we use this as a tool to help our students learn about adding and subtracting signed numbers? Okay, well, how do we instruct? Start at 0, students. We'll start at 0 and draw a nice vertical dotted line right at 0. That's what I have right here. See that? That's how you're supposed to start this project. So if you were asked to do using a number line to figure out how to get an answer for adding or subtracting signed numbers, you start by going to the 0 and drawing a dotted line vertical, just like this. Now, the first number I see there is 6. 6 is in this direction, so I draw a vector or a ray or an arrow, whatever you want to call it, and get to where 6 is and make a new dotted line. For example, if I was at 0, and the first number here was -2, I would put the dotted line here and draw an arrow coming back to say I traveled here. This was my first step. Does everybody understand? You know, you start at 0 with a dotted line and you go where the first thing tells you to go. Now, if you look right here, it says minus -9. So here's what we're going to do. We're going to show that we're going to go forward 9, and then we're going to come back 9. Now, this is the part where the students say, why? Why does minus -9 mean go forward 9 and come back 9? There's 10 different answers. You could say, I'm trying to show that you're subtracting a debt. I'm trying to show that the opposite of an opposite. There's a lot of different ways you could explain this, but what happens is when the students see -9, they imagine traveling 9 away and coming right back is the point of it. And when they travel 9 away, that mark that they make right there is the answer to the question is 15. So to be candid, my friends, I don't know necessarily if I would use this number line as part of my instruction. When it comes to using negative and positive integers, I prefer the colored model, the colored chips model. I think that's much better, but it's up to you what you think is better and which one you'd like to use, okay? For me, I would show this once or twice. I would deliver it with a big smile and that I believe in it and show it and support it and not let the students know that I don't like it. But I would focus a little bit more on the red and yellow chips. And those students who like the number lines, I would encourage them to keep using the number lines. But I could see looking at this up front, I have a feeling there would be less students being able to use this, whereas they would be able to be using the colored chips model that way. So the first dotted line is associated with the idea that 6 equals 6 plus 0. That second dotted line is associated with the idea that 6 plus 9 minus 9 is going to make 0. I'm sorry, it's going to make 6. And then that last line over there is the final line, which is 6 minus 9 is 15, is that last vertical dotted line. And if you read in the textbook, they explain it loosely. So maybe that's part of the reason why I'm not exactly thrilled with this particular version of how to teach it. Regardless, this is another example of how to show adding and subtracting signed numbers using a manipulative and a structure. So we have to be familiar with it as good teachers. Okay, my friends. In closing, we have a couple of important words we need to discuss. We have some terminology here on this slide and also on the next slide. There's some more talk about it. I just want you to be familiar with these words, and I'm not going to drone on about them, but they are words that you should know and that you should have a solid grasp on, especially if you are about to teach integers. First, the absolute value. There are a lot of ways to try to explain what absolute value is. The most direct and easy way is to just say, if it's negative, make it positive. That's what absolute value is. So the absolute value of 4, which is a positive number, is going to be just 4. The absolute value of 0, which is neither positive nor negative, is just 0. And the absolute value of -2 is 2. You'll notice that for every absolute value I find, the answer is positive every single time, or 0. Otherwise, it's not negative at least. And it doesn't matter whether I take an absolute value of a positive number or of 0 or of -2, I will never get a negative answer. What is the absolute value by definition? It's the answer to the question, how many units away from 0 is this number on the number line? How many units away from 0 is 4? 4. The answer is 4. How many units away from 0 is the number 0? 0. It is there, right? How many units away from 0 is -2? Here's 0. Here's -2. How many units is it? It's 2, isn't it? Okay. So you could either look at it like the original definition, which is answer how many units it is away from 0 on the number line, or you could just take the negative away if there is one, and that's kind of what most people do when they see absolute value. Take the minus away if there is one. And the main reason why we have absolute value is because there are times in mathematics where we need to express that a quantity must always be positive. And we can always make any quantity automatically positive just by putting these bars around them. And that's one of the main uses of the bars and the absolute value, okay? Next, we have the concept of identity and inverse. Identity and inverse show up here in arithmetic and in addition. They also show up in multiplication. They also show up in algebra when you study composing functions and determining an inverse of a function. You can find an inverse of a function if you take a function and if you multiply it by its inverse, you expect to get the identity. That concept of taking an element and joining it with its inverse to get the identity is something that is a common theme throughout many different studies in mathematics. For example, adding and subtracting integers has those properties to it. There is an additive identity. The additive identity, by definition, is 0. It's inarguable. It's not the kind of thing that you could say, well, for this case, the additive identity is no. The additive identity is always 0 in every situation. The additive identity is 0. The additive inverse would be that other element in the set that if I join it together with addition, with my element, I'm going to get the identity of 0. So for example, if my element is 9, the inverse would be -9 because 9 plus -9 is 0. If my element was -17, the additive inverse would be +17 because -17 plus +17 is the additive identity, which is 0. So the identity and the inverse have that interesting relationship that if you take any element in the set and join it together with its inverse, then it will yield the identity. In this particular scenario, the primary operation, the binary operation, is addition. That's why we're talking about the additive identity and the additive inverse. In the real numbers, the additive identity is 0, and that never changes. So we need to just remember that. And what you're looking at here is a lot of A and B variables speak to try to explain what the additive identity is and what the additive inverse is. If you try to follow it closely and look at each letter and interpret each thing it's saying there, it's saying basically the same thing I'm telling you in words as in a human conversation. The identity is the original thing. And if you have an element and you join it with its inverse, it should answer as the identity. That also works in multiplication, and we'll revisit that again on Thursday when we talk about the identity and inverse for multiplication for integers. And it also exists in algebra because functions have inverses. And if you compose a function with its inverse, you get the identity. The identity in algebra is x. Now, here are some important axioms. An axiom is like a theorem, but smaller. It's like a property. We have 3 axioms here to talk about. The first one is addition of signed numbers when both numbers have the same sign. If you add 2 numbers and they have the same sign, you can just add them and keep the sign. If you want to say that in terms of absolute values, here it is written out. Most students look at this statement, if both numbers are positive, then A and all that, and they kind of breeze over it because it's for the mathematician, and it's a little bit more advanced than is necessary. If you understand that if you add 2 negative numbers, it's the same as adding them and keeping the sign, that's what this is trying to say, using the idea of absolute value to make a perfect statement about it. In the next axiom, it says addition of signed numbers when one is positive and the other is negative. You may have heard before the statement, well, if they're opposite signs, then you just keep the larger sign. Remember hearing that? Like for a very basic example, if you had something like +4 and -7, right? If you were going to answer this question, you would subtract and you would get 3, right? But which one of these 2 numbers is bigger, 4 or 7? The 7, right? So the 7 is negative, so the answer is 7, negative. So the bigger number has the bigger sign. The answer is the same sign as the biggest number. So if you look closely at this, it's telling you that if the first one is bigger, if the absolute value of the first one is bigger, then you use a negative. If the absolute value of the other one is bigger, then you use a positive. And it's written in a complicated way right there with the less than and greater than signs, with the negatives, and all of this writing here. But the bottom line of it is what they're trying to say in all of this math speak is if it's different signs, then you subtract and keep the sign of the bigger number. For example, these 2 subtract to make 3. The bigger number is 7. Use negative because 7 is negative. That's it. The last one, which is subtraction of signed numbers, is you can think of subtraction as addition. So this question is the same as this question, but you can think of it instead as this kind of question if you assign a sign to each of the numbers in that way. And we have some examples here that you could use to kind of reflect on these axioms and to kind of make a concrete idea of it in your mind so that you're comfortable with it. And that's what we have for you guys for chapters 10.3 and 10.4. So what we're going to do now, my friends, is we'll take a short break, and we'll take a 15-minute break. We'll come back in 15 minutes. And after 15 minutes passes, I'm going to ask you to please go on into WebAssign, start chapters 10.3 and 10.4. And while you're doing it, I'll still be here with you because our class doesn't end until 9:15, and I need you to focus on this work now. So right now it's 8:37. I'm going to ask you to please return at 8:52. And when we get back, we'll have 15-minute break. When we come back, we'll start working on the WebAssign. And if people have questions, they can bring them up. Thank you for your attention in class today, my friends. We're going to stop our recording now, and we're going to take our break.